All right, so this lesson actually has quite a lot going on with it if you're unfamiliar with some of the core ideas of trigonometry with regards to angles and standard position. And so there's lots here, and I'll touch upon some of it. But ideally, some of these ideas sound familiar because there is a lot here to be introduced to. But before I go on, I'll just mention one thing, the phrase unit circle. That represents a circle with radius 1 centered at the origin. That's what we see right here. And anytime you see the phrase unit circle, we want to think a circle, clearly, but one with a radius of 1 centered on the origin, as you can see. And we see that phrase a lot. That said, I want to get straight to this, which is, as it says, an example of the unit circle. So I know that this circle here has a radius of 1. And there's an acute angle theta formed from the x-axis. So that acute angle theta they're describing must be this angle right here, from here to here. Because the other angle formed from the x-axis is from here to here, and that's not acute. So what is that angle? And we want to know both in degrees and in radians. So various approaches. If I just look at this visual here, I know this line here is the radius. So I know this has length of 1, and I know it goes to the point 0,6 and 0,8, which means that point 6 must also be equivalent. If I were to draw a straight line down here, I'll make it a little bit more colorful here. That point 6 must also represent the base of this triangle. So the distance from there to there must be 0.6. And this 0.8 must also represent the height of this triangle, which means I could use some basic trigonometry, right angle trigonometry, to determine that angle. And so I can see from angle theta, I have all sides of this triangle. I'm going to stick with just the points 0.6 and 0.8, so I can use the tangent ratio if I want. And I can see the tangent of theta equals opposite over adjacent, or in this case, the tangent of theta is 0.8 divided by 0.6. Now, what is that angle? At this point, I need my calculator, and I need to use the inverse tangent function. And there's various things I could do, but I'll just go straight to the inverse tan of, and I'll just type it in as 0.8 over 0.6, although it does reduce. Now, if my calculator is in radian mode, I will get an answer in radians. If my calculator is in degree mode, I'll get an answer in degrees. I'll stick with degrees at first. Easier to visualize, and so in degrees we get approximately 53.1 degrees. And just a quick little look at my visual, that seems sound, assuming this is drawn to scale. In radians, I could at this point just go back to the last lesson and take this answer in degrees and multiply by pi and divide by 180, or I could just go back to my calculator, put it into the radian mode, and find the inverse tan of 0.8 divided by 0.6, and we get approximately 0.927. The one in degrees is probably easier to visualize. It's almost certainly easier to visualize, but for other things, the answer in radians may be more helpful. All right, so that's the measure of the angle. That's theta. What's the tan of theta? I want this to be exact. Well, the tan of theta, I pretty much have worked out right here. The tan of theta is 0.8 over 0.6. And so just let me simplify this. The tangent of theta, well, it's not wrong to say 0.8 over 0.6. It's easy for me to simplify this to, for example, to 8 over 6. If I just multiply both by 10, divide both by 2, I get 4/3. And that's the best one there. Tangent of theta is 4/3. That's the exact value. That said, I want to use my diagram for this. Determine the coordinates of A if a half rotation, and we can think either in degrees or radians, it doesn't matter, was added to theta. So what does that mean? Well, let's look at this. And if I have this rotation, which you can see has been drawn here, if I add 180 degrees or pi radians, I end up with something right here, half rotation further on. And so I'll draw that right here. And so if I add pi, I'm going to stick with radians here to my original angle. This is where I end up, or if I add 180 degrees. So I can see there's a lot of symmetry here. This point that I'm now trying to figure out, which I'll call A prime, a little apostrophe, called the image point. I'm going to just label it like this. Well, I can see it's pretty much the same as A, it's just in the third quadrant, which means it must have the same values of A, but both those coordinates must be negative. So I have negative 0.6 and negative 0.8. All right, so next I have another unit circle. This time, I don't know the coordinates of A, but I do know that theta is pi over 6. All right, and so that angle I see right here is pi over 6, which, recall, pi over 6 is the same as 30 degrees. And so while I'll write pi over 6 here, you may find it easier to think about 30 degrees. That's it. I want to know the exact coordinates of A. So what is this point here? All right. Well, like before, I can imagine there being a right triangle here. So I'll draw a vertical line down. And like before, I know the hypotenuse of the triangle or the radius of the circle is 1. And so at this point, if I were to use my basic right angle trigonometry to find x or y, for example, I could say the sine of theta equals my y value divided by 1. Or I could say the cos of theta equals my x value divided by 1. X representing this distance from here to here, or the x-coordinate. Y representing this distance from here to here. If I do that, though, I won't necessarily get an exact value for both. And there's lots of approaches, but I will get an exact value for if I use sine to find the y value. So for example, if I say here that the sine of pi over 6, or the sine of 30 degrees, whichever makes you happy, just don't write the same thing out twice, I know that must be the same as opposite over hypotenuse, or in this case, y over 1, which means my y value must be the exact same as just the sine of 30. And the sine of 30 is exactly a half. Now, later on, we'll look more and more about how we can do actually all of this without a calculator. And if you're aware of your special triangles, then you have other options. But for now, I'll assume we're not aware of those. And we have access to a calculator, and that's exactly a half. So I got my y value. If I do the same thing for my x value, if I go the cosine of pi over 6 is x over 1, which is correct, I'll get an approximate answer for x. It'll be like 0.86 blah, blah, blah. So it's no longer exact. Now, some calculators will give an exact value, but I want to mention how I can do this on anyone. So at this point, to find that exact value for x, no, I don't want a decimal approximation. All I really need at this point is the Pythagorean theorem, because if I look back at this triangle, I now know y is exactly a half, and I've always known the hypotenuse is 1, so I have two sides of a right triangle. I can now find x using some pretty simple math. And so I can say at this point, if using the Pythagorean theorem, a squared plus b squared equals c squared, or in this case, it's x squared plus y squared, which is a half, squared equals the hypotenuse, which is 1 squared. That's quite nice. Pretty quickly, we get x squared equals 1 minus a quarter, right? A half times a half is a quarter, which is 3/4, which means x must equal the square root of 3/4. Now, I can tell here that x is a positive number. Just looking at the diagram, x is a positive coordinate. So while I really should say plus or minus root 3 over 2, because the square root of 3 is root 3, the square root of 4 is 2, while I should say that, at least initially, or should be aware that there's two possibilities to that equation, in this case, I can say I only want the positive version. So I only want this. And there's my x coordinate. And so altogether, the exact coordinates of A are root 3 over 2 and a half. And as I mentioned before, there's lots of other approaches. The more things you're familiar about already with trigonometry, the faster we can do this. If you're familiar with your special triangles, for example, we can be done with this in seconds. All right, next, for the second part of this, on the diagram, label the exact coordinates for each of the following angles. So the first one I have is pi minus theta. Now keep in mind, theta, we know, is 30 degrees, or pi over 6. So what would that look like? Pi minus theta, which means pi minus 30 degrees, or 180 degrees, I should say, minus 30 if you want to think in radians. Well, 180 degrees, or pi, is from here to here, but then we want to subtract pi over 6. We want to subtract 30 degrees. And so that would actually look something like this. It would be a reflection of what was given. And so this here, this is pi minus the 30 degrees, or minus the pi over 6. We have this. And that's the angle we're looking at, which means that coordinate of A will now change and be the same coordinates, but now it'll be in the second quadrant, which means my x value will be negative. It'll be negative root 3 over 2, but my y value will be unchanged. And so that's my answer for this. So I can say this would be negative root 3 over 2, but my y value would be unchanged. So that's for the first one. Next, what if I go theta plus pi? So going back here, I go back to my original theta, 30 degrees, or pi over 6. If I add pi, if I add a full rotation, well, then I just go all the way to here. And that's essentially what we did in our last question, which means I have a point in the third quadrant, but the exact same coordinates, just everything should be negative this time. And so on that point there must be negative root 3 over 2 and negative 1/2. Should have given myself a bit more space here. All right, and lastly, I have 2 pi minus theta, which in this case, keep in mind, is the same as 2 pi minus pi over 6, which if I want, I could simplify to 11 pi over 6. 2 whole minus a sixth is 11 sixths. That said, in terms of visualizing it, I can just look back here. And so imagine I have 2 pi, which is, let's draw an orange, all the way around here. That's 2 pi. But then take away a sixth. Take away a sixth of pi, or 30 degrees, which means I'm back to about here. And again, I have something that relates back to my first rotation. So let me clean this up a bit. And this rotation, that it looks like this, is 2 pi minus pi over 6, 2 pi minus the theta. And once again, we have a reflection of what we had for A. Must have the same x coordinate, so root 3 over 2. My y coordinate this time must be negative, just by looking at it. All right, I already wrote it down there. I don't need to write it down later on the other part. Last part. So now, new question. I have no visual, but I know this. I have some angle theta, and the sine of theta is 1/2. And I know theta is between 0 and pi over 2, which means theta is between 0 and 90 degrees. So going back to what else this visual, this angle in standard position, we call it, let me kind of visualize what this must look like. So I have I'll draw my x and y axis. And if theta is between 0 and 90, or 0 and pi over 2, theta is somewhere in here. It's somewhere in the first quadrant. But I also know the sine of theta is exactly 1/2, which means I can quickly go to my calculator and go, if the sine of theta equals 1/2, well, that means theta must just be the inverse of sine, which, if I think in degrees, I get 30 degrees. But I want to think in radians, because my restriction here was given in radians, so I'll say pi over 6. All right, so now I actually have a bit more to go on. I know my angle, the theta is pi over 6, and let me kind of draw, it's basically the same thing we had before. 30 degrees, something like that. All right, so theta equals pi over 6. All right, so with that said, I want to find the tangent of theta. Well, I have a few options. One option is to realize that I can look back just at a special triangle, if I have a special triangle. Another option, though, is to look up here and realize that tangent is always the same as sine over cos for that angle. And so just for variety, I guess, let me try that. And so if I want to find the tangent of theta, I can say the tangent of theta, which in this case is pi over 6. So what I'll say, the tangent of theta is the sine of theta over the cosine of theta. Or in this case, I can say the tangent of pi over 6 equals the sine of pi over 6 over the cosine of pi over 6. Which, if we look back to what we've done, I already know that the sine of pi over 6 is exactly a half, so I'll stick with that. The cosine of pi over 6, we actually already figured it out up here. The cosine of pi over 6 must be this root 3 over 2. If we look back at my visual, well, a lot of stuff here. We found out already that this is root 3 over 2. And recall from the beginnings of this lesson that the x-coordinate of this is equivalent to the cosine of that angle. And that's what's described in this visual right here. The cosine of any angle is equivalent to the x-coordinate of where that angle crosses the unit circle. Again, like I said at the start, there's a lot of things here. But I already know, therefore, the cosine of pi over 6 is root 3 over 2, so I can just use that and say, therefore, this is the same as 1/2 divided by root 3 over 2. And let's do a little bit of simple arithmetic here. We got 1/2 divided by root 3 over 2, same as multiplying by the reciprocal, so same as 2 over root 3. So multiplying by 2 over root 3, my 2's cancel out, and what do you know? We get 1 over root 3. So the tangent of this angle is 1 over root 3. Although, again, if you know your special angles and your special triangles, we could have done this a long time ago. That said, speaking of special triangles, special angles, they'll be a little more formally introduced in the next lesson, so hence just taking different approaches. That's it. We now know tangent is 1 over root 3. So what's the tangent of pi minus theta? Well, let's think of what that means. That means I'm looking not at this angle I drew in red, that is theta. I want to think about the tangent of that if I go pi minus that. So pi is from here to here. If it's pi minus that angle, I'm looking about right here, which, as we saw in the previous question, is just a reflection of what I have here, which means the tangent of this must be the same as the tangent of 1 over root 3, except in this quadrant, sine, cosine, and tangent may not all be, well, they will not all be positive, which brings us back to what we call the CAST rule. All trigonometric functions are positive in the first quadrant, only sine is positive in the second quadrant, only tangent is positive in the third quadrant, and only cosine is positive in the fourth quadrant. So because I'm looking in the second quadrant and it's only sine is positive, I know I'm going to have a negative value for tangent. Other than that, it'll be the same value that I have over here, but it'll be negative. So I can formalize it like this. I can say this will equal, or maybe I'll be a little more formal. So I can say the tangent of pi minus theta will be the exact same as just the tangent of theta, but with a negative. And the tangent of theta we saw is 1 over root 3, so this will equal negative 1 over root 3. So similarly, I want to do something for this, like this visually for the last one. I have 3 pi plus theta. So what does that mean? Let me clean this up a bit. Oh, not that much. There we go. So 3 pi is 1, 2, 3 180-degree rotations, plus an extra theta. Well, theta is 30 degrees, so now we're right here. That's what's being described, 3 pi plus theta. And once again, I have a reflection. I'm just in the opposite quadrant. And this time, I'm in a quadrant in which tangent is positive, which means the value of 3 pi plus theta, or 3 pi plus pi over 6, will be identical to this. It'll be positive 1 over root 3. So this will just equal the exact same as the tangent of theta, which we've seen is already 1 over root 3. So, like I said, if we're coming to this lesson with no real background in angles and standard position and all these things, this is a lot. It takes some time. Even if you come in with a good background, there's still a lot in this. And so we want to give ourselves time for this because this is pretty abstract, thinking about all these rotations, moving away from trigonometry with triangles.